must be singular matrices. If one of them is non-singular, then AB cannot be 0. Let us look into the proof. Let A not equal to 0, B not equal to 0, and let AB equal to 0. We have to prove that both A and B are singular matrices. Okay. Well, if possible, let A be non-singular. We have to show it is not possible. And we suppose that A is non-zero and B is non-zero and AB is 0. Well, when A is non-singular, we know A inverse exists. A is non-singular means determinant of A is non-zero, so that A inverse exists. Now, when AB equal to 0, I multiply both sides with A inverse, so that A inverse into AB is A inverse into 0. That is A inverse into A into B. Associative law. A inverse AB is A inverse A into B, and A inverse 0 is 0. Or IB equal to 0, or that implies B equal to 0. But what we assumed is that B is not. If AB equal to 0 and if A is not singular, then B must be 0, but we assume B is not 0, which contradicts the assumption that B is not 0. That shows A must be singular. Is it okay? When A and B are non-zero matrices, and if AB is 0, we have to prove that both A and B are singular matrices. Okay? Once again, let, if possible, let A be non-singular, so that A inverse exists. And when AB equal to 0, A inverse into AB is A inverse 0. That is A inverse A into B is 0, or IB equal to 0. That implies B equals 0, which contradicts the assumption that B is non-zero. Okay? Which contradicts the assumption that B is non-zero. Hence, A must be singular. Well, in the same way, similarly, we can show that B is also. How you show B is singular? We multiply with B inverse in the right side. When AB equal to 0, we write and multiply with B inverse, and the same we can write simply singular. So what we obtain is that if AB equal to 0, then either A equal to 0 or B equal to 0, or both A and B are singular. Well, it is a simple question. Now we come across with our main point of this section, that is to solve a system of linear equations by using matrix. Remember, by using matrix methods. Well, we can solve the system of linear equations in various methods without using any of this matrix or determinant, by eliminating one variable, by then eliminating the other variable, or substitution. We have a lot of methods to solve the system of equations. But here we are going to solve it by matrix. So we consider the system of linear equations. We have here 3 equations in 3 unknowns. Suppose we have 3 equations in 3 unknowns. Well, this can be represented as a matrix equation. We are going to represent this as a matrix equation. We are going to write multiply this matrix A1, B1, C1, A2, B2, C2, A3, B3 with column XY. When I multiply this and equate to this matrix equation, when I multiply this, you get A1x plus B1y plus C1z equal to D1. This equation. A2x plus B2y plus C2z equal to D2. That is second equation. A3x plus B3y plus C3z. So the given system of equations, we are representing in a matrix form, matrix equation. Or I can say simply AX equal to B. Look at AX equal to B, where A is the matrix of coefficients, X is the column matrix of variables, and B is the column of constants, column matrix of constants. So we are representing the given system of equations as matrix equations in the form Ax equal to B, where A directly taken from the coefficients, X is the column of variables, naturally always Y Z, B is the constant that is in the right side, that D1, D2, D3. Well, first we find determinant A not equal to 0. When determinant A is not equal to 0, then A inverse X exists. We'll discuss what happens if determinant A equal to 0. If determinant A is not equal to 0, then A inverse exists. What is A inverse? We know what is A inverse. It is 1 by determinant A into adjoint. So here, Ax equal to B, I am going to multiply with A inverse from that. Ax equal to B, I multiply with A inverse, I get A inverse Ax equal to A inverse. What is A inverse Ax? A inverse Ax is A inverse A, associative law. A inverse A into X equal to A inverse B. That is I. A inverse A is Ix equal to A inverse B, or X equal to A inverse B, where A inverse is 1 by determinant A into adjoint. So what we have is that X, the column of variables, we are going to get equal to A inverse B, where A inverse will be able to calculate 1 by determinant A. Looking once again, we have the system of equations. A1x plus B1y plus C1z equal to D1. A2x plus B2y plus C2z equal to D2. A3x plus B3y plus D3. Written as a matrix form, we have Ax equal to B, where A is the matrix of coefficients, X is the column of variables, B is the column of constants, and if determinant A is not equal to 0, A inverse X is, and multiplying with A inverse from left, we have the solution X equal to A inverse B. Well, hence we conclude, for the system of equations Ax equal to B, if determinant A is non-zero, the unique solution exists, because we have seen X equal to A inverse B. Earlier we stated, if determinant A is non-zero, we have A inverse X is, and due to that we are getting. So now we conclude, if determinant A is non-zero, we have unique solution, and what is that solution? X equal to A inverse B, where A inverse is 1 by determinant A. Well, this case too, when determinant A is 0, we go for adjoint of A into B. Well, this you only remember, don't go for a proof of this. If determinant A is 0 and adjoint of A into B is non-zero, there is no solution. The system is inconsistent. Whereas if the determinant is 0 and adjoint of A into B is 0, remember, if determinant is 0 and adjoint of A into B is non-zero, there is no solution. We conclude that the system is inconsistent. There is no solution. Whereas if determinant is 0 and adjoint of A into B, so when determinant is non-zero, we go for solution. If determinant is 0, we find adjoint of A into B. If it happens to be non-zero, no solution. If it happens to be 0, then there is no question of unique solution. Unique solution doesn't exist, but the system may have infinitely many solutions or no solution. It may happen. The system may have infinitely many solutions or no solution. Here, we put one variable as a constant, and remove one equation and proceed. Out of the 3 equations, we remove one equation. Then we will have only 2 equations. One of the variable we put as a constant and proceed with the 2 selected equations. We will proceed with an example later. Okay, let us solve using matrices. Be careful about the procedure. I can do one question in each. So here we have, I'm going to write this as a matrix equation. Ax equal to B, where A is the column of the matrix of square matrix of coefficients. X is the column of variables. B is the constant. Ax equal to B. Ax equal to B. Okay, first what we do, we find determinant. Determinant of A, can you calculate? That is 5 into minus 14 plus 72 minus 2 into 4 minus 24 minus 3 into minus 18 plus 21, and that happens to be equal to, right? The determinant is 321, which is not equal to 0. So this is the case when the determinant is non-zero, unique solution 6. When determinant is 0, we'll consider another. So what will be the unique solution? X equal to A inverse B, where A inverse is 1 by determinant A into adjoint of A. So we have seen the determinant is non-zero. Remember, the determinant plays a role later. 321, you have to remember it is 1 by determinant A into adjoint of A. So when determinant A is not equal to 0, you have to write this, hence unique solution X is, and what is X? A inverse B, where A inverse is 1 by determinant A into adjoint. Now our job is to find A inverse, 1 by determinant A. Determinant A we have 1 by 321. We have to find adjoint of A. How now to find adjoint of A? Can you recollect? We find the cofactor of each element. What is A11? That is minus 1 is 2. 1 plus 1, that is plus 1 plus minus 14 plus 72, that is 58. A12, that will be minus of 4 minus 24, that is minus of minus 20, that is 20. A13, so minus plus minus, sorry, plus minus plus, plus of minus 18 plus 21, minus 18 plus 21, that is 3. Okay, A21 is minus of 4 minus 27, that is minus 23, minus of minus 23, that is 23. A22, you have to be careful about the sign, plus minus plus minus. A22 will be plus of 10 plus 9, that is 19. A23 will be plus minus of minus 40 minus 6, that is minus 45 minus 6, that is minus 51, minus of minus 20, 51. A31 will be plus of 16 minus 21, that is minus 5. A32, calculated A32, that is minus 46, and A33 is minus 45 minus 4, that is minus 35 minus 4, that is 9. Well, once we have the cofactors, how will you write the adjoint? Can some of you tell me how you will write adjoint? Pradham, are you attending? Hello. Once we get the cofactors, we are going to write the adjoint. The first row, what we get, write at the first column. Second row, what we get, you write second column. Third row, what we get, you write third column. We got the adjoint. No need to go for cofactors and get the transpose. We can directly write. Once we get the cofactors, we get the directly write the adjoint. What we found in row wise, we write in column wise. Further, we found row wise, column wise. Further, we write third row, we write in third column. Once we get adjoint, what is now A inverse? 1 by determinant A into adjoint of A. Well, you can keep this constant outside itself. No need to take with individual. That will make it complicated. Let us keep the constant there itself. Now what is X? A inverse B. A inverse B. A inverse here. B, we have the constant 22 minus 16 minus 11. Now multiply. Let this be outside itself. First row, first column. First row, first column. So X means your X, Y, Z. 1 by 321 I am keeping as it is. First row, first column. Multiplication is here. 58 into 22. plus 23 into minus 16 plus minus 5 into minus 11. That is calculated to be 963. What is the second element? Second row in this column, 20 into 22 plus 19 into minus 16 plus minus 46 into minus 11, and that happens to be 642. And third row, 3 into 22 plus 51 into minus 16 plus minus 39 into minus 11, that is calculated to be minus. So what is the XYZ? So XYZ will be 1 by 321 into 963, 642 minus 320. Can you guess? Calculation very simple, which is nothing but 3, 2 minus 3, 963 by 321, 642 by 321, and minus 321. That is XYZ equal to 3 to 1, which gives the value of X equal to 3, Y equal to 2, and Z equal to 6. Well, getting clear, my dear children, how to get the solution by matrix method, right? We write the equation in matrix form first of all, right? We write the equation in matrix form, and first what we do is, after getting matrix form, we get the determinant. Once the determinant is non-zero, we conclude that the unique solution exists. That is x equal to A inverse B, where A inverse is 1 by determinant into adjoint of A. We have determinant A with us. Adjoint of A we calculate. We calculate very carefully. First row we write here, then second row we write here. While writing the cofactors, we take row wise. Third row we write here, and further when we go to the adjoint, whatever we are written row wise, we write in column wise. We get the adjoint. Once we get the adjoint, we have A inverse is 1 by determinant into adjoint of A, so that x equal to A inverse B, that is A inverse. I keep the constant outside itself for convenience. Later I will take inside. X, Y, Z equal to A inverse into B. We multiply, we get A inverse B. Now we may sometimes encounter fractions also. Luckily we have integer solution here. X equal to 3, Y equal to 2, and Z equal to minus. Okay. Well, will you note down questions here? Solve using matrix method. This is normally coming for 6 marks. This question number 3 by equations of 3 unknowns and 3 equations normally comes for 6 marks. If it is 2 unknowns and 2 equations, it may come for 4 marks. So note down the question. Well, here we conclude the session. Shall I conclude and go to meeting? We'll try for a while whether it is successful or not. Okay. Well, we'll try with go to meeting.